Hi everyone, warm welcome to B.Tech. Let us interlink these Young's modulus E and Poisson's ratio mu to a three-dimensional state of stress, and let us try to derive the stress in x, y, z directions with respect to Young's modulus E and Poisson's ratio mu. Let us try to derive the strain in x, y, and z directions with respect to these Young's modulus E and Poisson's ratio. Let us derive this now. See, we have a three-dimensional object which had undergone to triaxial stress, that is sigma x in x, y and z directions respectively. So if I want to find the strain in x direction, let us, for example, if sigma y and sigma z are not there, so what is the strain in x direction? So we know strain in x direction is equal to sigma x by Young's modulus E, right? Okay. So strain in x direction is equal to sigma x by E, right? Fine. Then if I try to find the strain in x direction, I will get a very big equation. If I include sigma y and sigma z, how this is? See, this is very easy to remember. See here. So if I am applying stress in x direction, so what is going to happen? Okay. So because of this stress in x direction, okay, I had got a strain in x direction, right? Yes. And because of this stress in x direction, there is some strain in y and z directions also. Because of the stress in x direction, I am getting strain in y and z directions also. How? Why? Because of the property of lateral and longitudinal strain. So I am applying stress in x direction, there will be change in dimension of y and z directions also. So to find the strain because of stress in x direction, to repeat, to find the strain in y direction because of stress in x direction. So just writing here, strain in y due to stress in x. So how to find this? Strain in y because of stress in x, property lateral strain. So we know lateral strain is equal to mu into, right, longitudinal strain. Okay. So what is the longitudinal strain here? So the longitudinal strain will be epsilon x. So because of strain produced because of stress applied in x direction, okay, the strain produced in y direction will be, okay, minus mu sigma epsilon x. Okay. So the same will be produced in x direction also. The same will be produced in y and z direction. This is in y direction, so this is in z direction. If you see here, epsilon x is equal to sigma x by E. So what is the sigma x by E? This is a direct strain or longitudinal strain applied because of stress in x direction. Okay. What is this mu sigma y by E? This mu sigma y by E is because of we had applied stress in y direction. So let us write in tabular form. So if I interlink it in tabular form, so let us take directions x, y, z, and I am applying stress in x direction, stress in y direction, stress in z direction. Okay. Because of applying stress in x direction, I am getting strain in x direction as epsilon x, and I am getting strain in y direction as, okay, remove negative, mu epsilon x and mu epsilon x. Okay. So because of applying stress in y direction, I am getting strain in y direction and longitudinal strain in y direction and lateral strain here. And similarly, because of applying stress in z direction, I am getting a normal strain in z direction, and I am getting what we call strain in x direction as mu epsilon z and mu epsilon z. Okay. So if you see here, what is so how to write now? I want to find the strain in x direction. So this is the strain in x direction. So this is the strain in y direction. So this is the strain in z direction. So just interlink the formula. So strain in x direction is equal to epsilon x. Epsilon x means sigma x by E. So sigma x by E, and if I have to add this term also, okay. So this is strain in x direction. This is, so I have to add mu sigma mu epsilon y. So mu epsilon y means then again sigma y by E. So epsilon y means sigma y by E. So sigma y by E, y minus because of in the direction the dimension is reducing, that is the reason minus. If I am applying the stress in x direction stresses will be positive, y and z direction stresses will be negative. Okay, so negative here. This one is also mu epsilon z. So epsilon z means sigma z by A. The same thing I had written here. Y minus because of the stress reduced in, because of the strain, there is negative strain in z direction. Now we have to find epsilon by strain in y direction. So strain in y direction will be, okay, so sigma epsilon y and summation of mu epsilon x and mu epsilon z. So epsilon y means sigma y by E, and epsilon x means mu epsilon x means mu sigma x by E. Mu epsilon z means sigma z by E. Y minus because of applying stress in y direction, there will be only increase of length in y direction and there will be decrease of length in x and z directions. So negative for x and z directions. And similarly, if I want to find a strain for z direction, so I have to add epsilon z, that is sigma z by E, and I have to add mu epsilon y, that is mu sigma y by E, and mu epsilon x, that is mu sigma x by E, and there will be minus signs for these. Why? Because of there will be some increase in dimension in y and x directions when you are applying stress in z direction. And you can say the minus y minus had got, because you can write Poisson's ratio mu is equal to strain in minus strain in lateral by strain in longitude. Okay, so whenever the longitudinal strain is increasing, the lateral strain will definitely get reduced. That's why we use minus here. So all my mu, that is all my lateral strains will be negative. So that we got negative here. We can interlink in both ways, because of the only assume one way. Don't interlink both. Either assume that direction strain has got reduced, so you have used negative, or assume that there is negative in the formula of Poisson, so that this is the reason we got negative here. So this is the very important formula you have to remember for the strain in x, y and z direction, right? So there is one concept known as principal strain. So principal strain means nothing but because it exists because of principal stresses. There is no shear stress. If there is no shear stress, we can name those directions as principal stresses, that we can discuss coming classes. So if I want to write the strains in principal strains, so just instead of writing x, y, z, you use 1, 2, 3. So those are the only directions. 1, 2, 3 we have principal directions. So we can interlink those as epsilon 1, epsilon 2 and epsilon 3. Next, so for example, if you have any two-dimensional strain, so equate the stress in z direction to 0, okay, and if you write these equations, so we will get these three, okay. So don't like assume that a two-dimensional strain means there will not be strain in any z direction. No, there will be strain in z direction. Why? Because of if you are applying, there might be stress 0 in x direction, but strain is not 0. Why? Because of you are applying stress in x and stress in y. So there will be some lateral strains because of this x and y in that direction. And so after that, the same equation we had got here. So if I applied the same principle, like if I am taking only 2D stresses, that is sigma 1 and sigma 2, if I equate sigma 3 equal to 0, so I will get these equations. From that I can write sigma 1 and sigma 2 like this, right? We had one more topic known as hydrostatic stress. So it is very simple, similar to my three-dimensional stresses, but the logic here is the term hydrostatic is used to describe the state of tensile or compressive stress that is equal in all directions. So it is generally the stress is equal in all directions. So at a particular point, the stress is equal in all directions. So this is our epsilon 1, epsilon 2, epsilon 3. So we will add this and we will get one equation in the form of sigma 1 plus sigma 2 plus sigma 3 into 1 minus 2u by E. So volumetric strain is equal to the change in volume dimension by original volume. So we can interlink this, we will to get volumetric strain formula. And we had plane strain and plane stress conditions, that is only plane strain means we will only take one plane and we will try to find the strain components. So you know that one plane, the three strains will also exist. So that is a plane strain condition, plane stress and plane strain conditions we have generally. And let us try to find the stress strain relations for different materials. So for linearly elastic material, it will be straight line. Why? Because of it will follow Hooke's law. So y proportional to x, so y equal to mx, you will get a straight line, and c is 0, so the line will pass through origin. So this graph is for linearly elastic. This is generally asked in for objective questions, and you might also ask to draw stress strain diagram for different materials. So this is the linear stress strain diagram for elastic material, and this is for rigid material. Okay, so the rigid material means rigid body. So the distance between 2 points in a rigid body remains same. So the distance remains same even though after removal of load. Also there is no concept of strain. So what are the stress you take? You take what are the stress. So simply strain is 0. Next, so for a perfectly plastic one, so the stress strain graph will be parallel to the strain line. Okay, so for perfectly plastic and for rigid plastic, so plastic region there will be some amount of strain hardening. So this is the graph, and for elastic perfectly plastic, so this is the graph looks like. So elasticity is there and plasticity is also there. Okay, and the plasticity is perfectly plastic, so it will get horizontal line. If it is not perfectly plastic, we will cut a curved line. That is the logic you have to remember here. Okay, so these are the elastic like stress strain graphs for different materials. Now let us see what is meant by isotropic property and homogeneous property. So this is very important property while studying strength of materials. So isotropic property means, so at a point the material properties are equal in at particular point. For example, if I take modulus x, Ex, Ey and Ez, okay, so all these material properties are equal at a particular point, then such a property is known as isotropic property. And homogeneous means for all points in only one direction, metal properties are equal. In only one direction, either it may be x or y or z, metal properties are equal. And isotropic means at a point in all directions, the stresses, the metal properties are equal. For homogeneous material, for all points in one particular direction, the metal properties are equal. This is about isotropic property and homogeneous property. So we will continue the remaining things in next session. Thank you.